Hi everyone, this is Sreelakshmi P from Msc.Ed Physics, and I am today here to explain the phase transition and pre-critical phenomenon in case of liquid crystal, in particularly Msc.Ed. So when we look at the phase transition, let us consider the basic things. Okay, so we know that the liquid crystalline mesophases are divided into three, right? One is nematic, second one is smectic, and third one is hexactic. Okay, so what is phase transition? The basic meaning, it is the physical transformation between various states of matter, correct? If something is changing from a solid to liquid or liquid to gas, we say that there is phase transition of that particular matter. So what happens here is, when the phase transition is happening, there is certain changes that happens in macroscopic properties also. It is not only the shape, the figure, or the volume, as we say for the matter, like phases of matter, we say there are changes in macroscopic properties too. So here what happens particularly in case of liquid crystals is, the molecule sits on planes with interplanar spacing about equal to the molecular length and with the long axis perpendicular to the plane, correct? That is how we have already learnt about the arrangement of the layers in a liquid crystal. The changes, the directional changes in them causes the different phases like nematic, smectic and hexactic. And here we say there is something called density wave, which is already dealt by my other friends, which is characterized by amplitude and also phase. Now let us look into smectic A, because we are going to explain the things with reference to smectic A, what happens to the smectic A phase. So as we see the smectic A phase, the molecules will be arranged in layered structure, and the speciality is the layer thickness will be identical to the full molecular length, as we said. Okay. Also within the each layer, the center of mass of molecule is no longer having a long range order, and each layer is individually a dimensional fluid. So even if I take each single layer in smectic A phase, I can consider it as a two-dimensional fluid. And okay, also for this fluid there will be a probability of interlayer diffusion, like the layers can be diffused and also the molecules are arranged parallel to the smectic layer, and the symmetry is given T2 into dt, and then in this phase the average molecular orientation is perpendicular to the liquid layers. Okay, next one we'll go into transition. What all kind of transition happens within smectic A? Okay, the first one will be considering smectic A to smectic C transition, and the other one will be smectic A to the isotropic phase transition. Okay, when we say the temperature is further decreased, I mean if I am getting the smectic A phase in a particular temperature, I'm decreasing the temperature. Okay, I have a particular temperature for smectic A, now I reduce the temperature. What will happen? The smectic A phase will transform into a phase possessing even lower symmetry. So the symmetry of the smectic C phase will be lesser than that of the smectic A phase, and the breaking of D symmetry will lead to the appearance of tilting of molecules relative to the smectic layer. So if I look into the molecules with respect to the smectic layers, I will feel that these molecules have tilted than that of they were arranged in smectic A phase. Fine. And the phase thus derived is called smectic C. So this new phase which I got when I lowered the temperature is called as smectic C phase, which possesses the symmetry as given. Okay, and it has a lower symmetry compared to the smectic A phase, as we already explained. Next one is the tilted molecule picks a special direction in the smectic plane, that is their projection in the xy plane aligned along a common direction denoted by a unit vector C called C director. So we know that all these particular molecules are tilted, right? So I cannot use the axis of the plane to consider on which axis the tilted molecules are placed. So here I'll use a unit vector called C, and it is called as C director, right? Next, this is a picture of smectic A and smectic C phase. Whatever we have explained, this just sums it up all. Okay, the first one is smectic A. See, the molecules are arranged in the direction of K and N. The directrix simple, right? The smectic A layers and both are perpendicular also. Here there are three two-dimensional fluid layers, right? The first layer is there, and here is the first layer is there, and also now we can see the second layer over here and third layer over here down. Fine. When I am lowering the temperature, what happens? We know that the smectic A phase transits to the phase of smectic C. So what happens in smectic C? The molecules in each layer, see, it is not only for a single layer, the molecules of each layer gets tilted. So it is tilted into a right side here when we see. So now the direction of or the axis of the molecule is not same as the axis of the layers or the perpendicular one, right? The perpendicular that I have drawn from the layers, it's not the same. So here what happens? Here N that we see, that is, we have already called it as C director, in the sense in which axis this particular tilting has happened to the molecules inside it. Okay, so this is clear, smectic A to smectic C, the easy one. Next one is the transition from smectic A to the isotropic phase. Okay, the first one we explained was happening when I reduce the temperature. So here what I'll do, I'll increase the temperature. Okay, so when it reaches sufficiently high temperature, this smectic liquid crystal has high tendency to go into an isotropic phase. Okay, so what happens? Both the positional and orientational order are lost and the material becomes isotropic like a conventional fluid. So here in smectic C also, smectic A also, there was a particular direction that this molecule will be arranged. Okay, but when I am increasing the temperature sufficiently and going on, at a particular temperature what happens? All this order, all this position, all this director, everything gets loses and it becomes a conventional liquid. And then we say that it is isotropic phase. So we say that this isotropic transition happens only at very higher temperature when compared to the transition between smectic phases or the nematic phases. So even for smectic A to smectic C phases, there is no much temperature reduction. But here what happens? We have to supply a higher energy or temperature. Yeah. And next one is, at the transition temperature, the long range ordering present in the smectic phases breakdowns completely. So there is a particular temperature called transition temperature where this transition completely occurs. Therefore, the long range order, we know that the order will not be further followed. Long range order will be as a whole destroyed. Fine. Now we get into the thermodynamical aspects. Okay, we know that there is a temperature at which the transition occurs. We call it as transition temperature or critical temperature. Fine. So we know that the free energy is very important in thermodynamical aspects in any matter. So the free energy associated with the smectic phase become equal to that of isotropic phase. Fine. So what happens below transition temperature or critical temperature and above? So below critical temperature, the smectic phase is stable, in the sense if I am reducing the temperature below Tc, that is my critical temperature, it can maintain the level of smectic phase. At the same time, at higher temperature than critical temperature, the isotropic phase become energetically favorable, in the sense it has a tendency to go towards the isotropic phase. And the smectic to isotropic transition is driven by entropy rather than that of the enthalpy. Why? Because we know that due to the change in the temperature, the order or the symmetry and whatever kind of things it had in relation with the entropy has already destroyed us, or it has already gone away from that of the smectic phases. In that high temperature, the entropy associated with the disordered isotropic phase become dominant. Yeah, that is why we say that entropy is more driven in case of isotropic transition, leading to a decrease in the free energy of the system. And now when we see in smectic phase, the molecules are confined to layers. Correct. We had the specific layers. We could say, okay, there are 1, 2, 3, 3 layers, 4 layers. How many number layers it had? Like two-dimensional fluid. Each layer we could specifically associate it. Correct. But here what happened? The molecules are in isotropic phase. It allows for unrestricted molecular motion. That is why we say it is basically moving into a liquid phase, a whole liquid phase, leading to a substantial increase in the configurational entropy. This is the reason why the entropy drives the smectic A to isotropic transition rather than that of the enthalpy. Right? And at the critical temperature, what happens? The entropic gain associated with the molecular disorder overcomes the enthalpic penalty of disrupting. That means I know if this magnetic structure is more ordered than that of the isotropic structure, correct? So there must be an energy which holds all this orderedness together. So only when I cross this particular orderedness, I can go into the isotropic form, correct? And it is at this critical temperature that the matter requires enough energy to cross this orderedness. That means it will cross this enthalpy penalty of disrupting the ordered magnetic field, that I have to destroy this magnetic structure in order to move into the isotropic structure. Fine. That happens at the critical temperature. So when I cross this ordered magnetic structure, what happens? My entropic gain increases. In the sense, my entropy itself increases, in simple words. And when we look into the experimental techniques, we use differential scanning calorimetry, X-ray diffraction, optical microscopy and dielectric spectroscopy to study this magnetic to isotropic transition. So here is one simple picture which represents the transition. So here is magnetic A phase. So in between what happens, it goes similar to the nematic phase, and at critical temperature what happens? The isotropic. Here, see the first one, magnetic A. Magnetic A has a layer, two layers, correct? And even though there is distortions in the molecule, they almost have the same behavior of movement or arrangement. When it comes to the next one, the temperature is going increasing. It shows similar to that of a nematic phase, that it is moving around. And when it crosses the critical temperature, what happens? It completely disrupts the orderedness and it goes to the isotropic phase. Fine. Now we'll get into what is pre-critical phenomenon. So what is pre-critical phenomenon? When we look at the word structure itself, pre-critical phenomenon. So something that is happening before something, right? The critical phenomenon. So it is a behavior exhibited by a material just before it undergoes the transition. So we know that there is a particular temperature where this material undergoes to magnetic phase A to the isotropic phase. So what kind of behaviors does this particular material shows just before this transition? That is what is called pre-critical phenomena. Okay, this pre-critical signifies the stage of the material approaching the critical point of the transition to. Okay, so some of the pre-critical phenomena are the divergence of correlational length, specific heat, something happens in specific heat, and also there is some speciality in case of susceptibility as the transition point. Okay, and why is the pre-transitional behavior of magnetic liquid crystal important? Because it helps in elucidating the mechanisms driving the phase transition, because we need to know how these phase transitions are happening and what all are the significance of it, or why we need it. So to elucidate all this, to get to the conclusion of all this, we need to know what is the pre-transitional behavior. And one more use is that for predicting the properties of the resulting phase. Okay, if I know that these are the some behaviors exhibited by a particular material before it goes into transition, then there is high chances that I can predict how it would behave in the coming transition or coming phase. I'm going to the particular material. If I am the material, I'm going to some other phase, but before that I show particular characters, like which is not so common. So observing that, someone can predict how I will be behaving in the next phase. Okay? And there is studying of the precursor effects and fluctuation. Precursor effects is nothing but the pre-transitional, what you can say, the concepts and all the behaviors itself, and the fluctuation in the pre-transitional temperature range. Okay, so there is a transition temperature, right? TC, critical temperature. So it is not, we are not directly going to the TC. There is a variation of temperature. There is a range of temperature where this transition can happen. Okay, so the researchers were keen into that, and they studied on that, and therefore they got into the idea of dynamics of phase transition and the role of thermal fluctuations and the stability of different magnetic phases also. Okay, so your precursor effect, to be precise, is the phenomenon where substance exhibit properties of the next phase. Yeah. So what happens? We know that some pre-transitional behavior is occurring, correct? So if that material shows the behavior that it would show after the transition, then we show that okay, this material undergoes precursor effect, or it shows precursor effects. Okay, it could be involving the alignment of or ordering of the molecules resembling to those of the liquid crystal phase before the transition occurs. And this effect is very significant in understanding the phase transition and the behavior of liquid crystal in the whole material itself. So moving further, we have already said there are some behaviors. So some behaviors are this fluctuation in density, specific heat, and other thermodynamic quantities. So there are some behavioral changes that is happening, or specific behaviors that is exhibited by this liquid crystal just before it goes for transition. So what happens in fluctuation in density? Just get into look. Okay, so before a phase transition, the density of material may exhibit fluctuation. What happens just before going in? There is a fluctuation, variation that is happening in case of the density. Fine. And what happens? The fluctuation arises from, why does this fluctuation happen? So from what does this fluctuation happen? It arises from the interaction between the molecules as they start to rearrange themselves in preparation for the transition. Since this material has to get ready, okay, I have to get ready for the transition, then the interaction of molecule will lead rise to this fluctuation of density. And near the critical point, the fluctuation becomes more pronounced. That means it becomes more predominant. Okay, at the critical point, what happened? The transition happens. So I know, okay, this critical point is reaching. Now there is my interaction between the molecules are high. Therefore, the fluctuations is very predominant. Okay, and next one is specific heat fluctuation, as you see here over here. So specific heat, what is specific heat? It is a measure of the amount of heat required to change the temperature of a substance by a certain amount. Correct? We say that 1 degree Celsius and all. So before phase transition, what happens? Specific heat may exhibit fluctuation. Similar to density, this also will have the structure, due to the structural changes that is undergone by the molecules of that particular material. What happens? The specific heat also shows variation. Okay. Next one is susceptibility fluctuation. So susceptibility refers to the extent to which a material responds to an applied external field, because we have already studied in case of magnetic susceptibility, etc. Right? So before a phase transition, susceptibility may also vary. Why? Because the molecular, we know that the susceptibility is dependent on how the molecular arrangement is correct, or how they respond to an external field. So when the molecular arrangement is deferred or varied just before the transition, what happens? The susceptibility also varies or fluctuates. So therefore, when we observe this fluctuation, if I study the fluctuation, it can indicate the material's increasing sensitivity, correct, when the external field is applied and when it reaches near the critical temperature. If it shows a very high response towards external field, then I can know that the material sensitivity is increasing to the external influences. That means external fields that is we have provided to it. Okay? And here are the references that I have gone through, and I hope the whole lecture is clear for you. It is not much of a confusing one, how the phase transition happens, which all kind of transition we have gone through, and what are the pre-transition or pre-critical phenomena. Pre-critical phenomena basically refers to the phenomena that is shown just before the transition. So this is all about this presentations. I hope it is all clear and well. Thank you so much.